What's up, guys? Today's video is going to be on taking roots and on rational exponents. Okay, and I want to click through the notes again. I'm going to just kind of skim through it. Feel free to pause it and write this down. You should have gotten this in class already, but if you're watching this early or if you're not in my class and you're watching this video, feel free to pause it and write these notes down. And then at the end, I'm going to do some examples where I focus on the techniques that I like to use. Okay, so first of all, we have to understand our vocabulary. We know this is called a radical sign, and typically you don't see a number here because you're used to seeing square roots, but there are roots other than square roots. There's third roots and fourth roots and fifth roots, and the number here we call the root, or sometimes called the index, tells you which root you're taking. The part under the radical we call the radicand, although usually I'll just say the part under the radical. So to simplify a radical, you factor the radicand completely, circle groups of like factors the size of the root. So if we're taking a square root, then we're going to circle groups of 2. If we're taking cube roots or third roots, then we circle groups of 3, and so on. And then for each group that you circle, you take them out of the radical and you multiply them on the outside of that factor. Okay, I don't use this method personally, but a lot of people do, and I am going to show you how to do it here. So for example, if you've got the square root of 32, and remember, for square roots, you don't really need to put the 2 here. Well, 32 can factor this way. 2 times 2 times 2 times 2 times 2. And I didn't draw it here, but you can do a factor tree where you start with 32 and you break it into 2 and 16. You break the 16 down to 2 and 8. And you keep breaking things down in a tree until you've got nothing left at the bottom but prime numbers. If you do that, what you'll be left with is 5 2s. Okay? That's because 2 to the 5th power is 32. So once it's factored completely, we're going to go back and circle groups of 2. Like groups of 2. So you've got a pair of 2s here and a pair of 2s here that are circled. Okay. Now for every group you circle, you pull 1 out. So I circled a group of 2s, I pull 1 2 out. I circle a group of 2s, I'll pull 1 2 out. Now these go away on the inside, but on the outside I'm going to have 2 times 2 out here, which is 4. And there's 1 2 left behind. So every group you pull out, they go away on the inside and you put 1 of those on the outside. So for 108, again, if you factor it all the way down, and I'm not showing you the factor tree here because personally I don't prefer to use this method, but if you use the factor tree for 108, you will get down to 2 times 2 times 3 times 3 times 3. These are all prime numbers. I can't break these down any further. They're only divisible by 1 and themselves. And if I multiply these together, I get 108. Okay, so again, now I'm looking for pairs or for groups of 3. Instead of pairs, I'm looking for groups of 3. I don't have 3 2s, so I can't do anything with those. But I do have 3 3s, and I'm going to circle that one group of 3s, and for that whole group, only 1 3 comes on the outside. Okay, the 2 that are left, I multiply back together and get 4. So everything that gets pulled out gets multiplied together, and everything that gets left behind gets multiplied together in your final answer. But remember, for the whole entire group of 3, just 1 3 comes out, okay? Because remember that a third root is saying, you know, what number would I multiply 3 times to get this number? Well, I've got 3 3s right here. So the number that I'd multiply by itself 3 times to get 3 times 3 times 3 is 3. You're taking the third root of this. Because you have 3 of them here, we're taking the third root and putting it on the outside. All right, so let's talk about my method that I like to use. And the notes look a little funny here. Sometimes this is in a browser. If you actually open it in PowerPoint, it wouldn't be messed up like this. So for my method, it says look for the greatest factor of the radicand that has a perfect root for the root in the problem. So let me just jump down here to this first example. And these are the same numbers we just used. The way I like to answer the question is this. Can I take the square root of 32? Is 32 what we call a perfect square? Meaning, is there some integer, some whole number that I can multiply by itself that will give me 32? There's not one, right? Like 5 squared is 25 and the 6 squared is 36. This is in between the two. So there's no whole number I can square to get 32. So then the next question I ask is there a factor of 32 which is a perfect square? Okay. So over here I have written out, this is just the numbers 1 through 10. Okay, and this was supposed to say x squared, but the notes are kind of messed up. This should say x squared, and this should say x to the third. And so these are all the squares of these numbers, and these are all the cubes of those numbers. So this is 2, so you've got 2 squared and 2 to the third. This is 3 squared and 3 to the third. 4 squared and 4 to the third. So these are the perfect squares, and these are what we call the perfect cubes. These numbers can all, if you take their cube root, you get a whole number. If I take the cube root of 512, I get 8, for example. So the question then is there a square root? Is there a factor of 32 which is a perfect square? So just go to your perfect squares column if you don't know this already and think, which one of these numbers are factors of 32? Well, it can't be any of these numbers because they're too big. These are all bigger than 32. Can I divide 32 by 25? No, it's not divisible. Can I divide 32 by 16? Yes. So you not only want to pull out a perfect square factor, you want to pull out the biggest one you can, and the biggest one would be 16. I can write 32 as 16 times 2. You would agree with that, right? 32 is the same as 16 times 2. Well, 16 is a perfect square, and I can take the square root of 16. What is it? It's 4. So I pull the square root of 16 out and put a 4 on the outside. And this was the same answer we got before, but it happens a lot faster. Now, the difference here is you save some time because you're not having to draw the tree out and do all that prime factoring. On the other hand, you've got to be familiar with your perfect squares and your perfect cubes. So you need to try to memorize most of the perfect squares and perfect cubes, at least go up to, 6 or 7 to down here. And it wouldn't hurt to know some of the powers of 4, or at least recognize that something is a power of 4 or that it is a power of 5, even if you don't know exactly which one it is. All right, so another example, the cube root of 108. Is 108 a perfect cube? Well, you look in my column over, you can see that it's not. If you don't know this already, look here and see that it's not, okay? But can I divide 108 by one of these numbers? Certainly I can't divide it by anything bigger than 108, but can I divide it by 64? If you have to, put in your calculator, you'll see that you can't. Can I divide it by 27? Actually, I can. 108 is 27 times 4, okay? So now I've pulled out the biggest perfect cube factor of 108. The biggest factor of 108 that's a perfect cube is 27. And what is the third root of 27? It's 3. 3 times 3 times 3 is 27. So when I pull that cube root out, put it on the outside, the 4 is left behind. The nice thing here is you don't have to do a bunch of multiplying of stuff. You're pulling one thing out and you're done. Okay? So that's the method I like to use, and we'll work some examples here in a minute. All right, we're going to talk about rewriting between radical and rational exponent forms. Okay, and simply, this is what it means. If you've got in this case, it's the fifth root of 32 to the third power. You can rewrite it this way, 32 to the 3/5 power. So what you need to know here is when you have a rational exponent, an exponent which is a fraction, the numerator, the number on top, is the power, and the number on the bottom, the denominator, is the root. Okay, just like that's the root and this is the power. So the 5 goes to the bottom and the 3 goes to the top. So when you see 32 to the 3/5 power, what that's saying is that's 32 to the third power, and then you take the fifth root. Or you could say in the other order, it's the fifth root of 32 raised to the third power. It looks really crazy to talk about raising a base to some fraction power, but it's actually really simple if you think about it one step at a time. And that's what we're saying here. You can evaluate rational exponents by doing them one step at a time. So if I say 32 to the 3/5 power, that sounds crazy. Wow, we're going to do 32. It's already a big number. We're going to raise it to the 3/5 power, which who even knows what that means? Well, you do it one step at a time. What is the fifth root of 32? Well, actually, that's just 2. 2 to the fifth power is 32. So if I take the fifth root of 32, that's just 2. Notice the 5 went away, and I've just got a 2 here. And what's 2 to the third power? That's 8. So I always say take the root first, then raise it to the power. You want to get smaller before you get bigger. Because if I had to do 32 to the third first, I get some really big number, and I may not know how to take the fifth root of that. Okay, here's another example. We have a negative base this time. Okay, again, second power, third root of negative 8. Well, I'm going to take the third root. Now, the third root of 8 is 2, and since it was negative, it stays negative. As a side note here, you can take odd roots of negative numbers, and they keep their signs. You cannot take an even root of a negative number, or you get an imaginary result. That's how you get I, if you remember from last year. So we can take odd roots of negative numbers and get a negative result, just like we can raise a negative number to an odd power and get a negative result. It just keeps its sign. So when you take the third root of negative 8, you get negative 2. Negative 2 to the second power is positive 4. If you're putting this in your calculator, and I don't know why you are, but if you are, you better make sure you're putting that in parentheses, because that negative sign has to go with it. If you just type negative 2 squared in your calculator and you don't put parentheses, you're going to get negative 4. And the calculator is actually going to be right, because if you don't put parentheses here, the square only goes with a number, not with the sign. It doesn't take the sign with it. So you have to make sure that you put it in parentheses if you intend to square the whole number, which we do in this case. So it's 4. Okay, so now I'm just going to do a couple examples. So first we're going to simplify the square root of 150. First question you should always ask yourself is, can I just take the square root of 150? And the answer is no. There's no number that I can raise to the second power, no integer, no whole number that I can raise to the second power and get 150. So the next question I ask is there a factor of 150 that's a perfect square? Or what's the biggest factor of 150 that is a perfect square? So think back to your perfect squares. Let's just write a few out. 1, 4, 9. I'm on the screen. 1, 4, 9, 16, 25, 36, 49. You can keep going. 64. But are any of these, once you get past the halfway point, by the way, you can stop, because the biggest factor of a number other than itself is always going to be half of itself. So once you get past the halfway point, we don't need to keep checking. We're past the halfway point. So as I go down this list, what's the first number I see that I can divide into 150? And it's not any of these. It would be 25. Okay, 25 does go into 150. How many times does it go into 150? 6 times. So it's 25 times 6. Okay, you agree that 25 times 6 equals 150. Then I'm going to pull out any perfect square factors, which was this 25 that I found. I'm pulling that out as a 5, right? The square root of 25 is 5. So what that leaves me is 5 times the square root of 6. And that's the answer. Now for the third root of 40, think about your perfect cubes. Okay, 1, 8. These get pretty big. So 1 to the third power is 1. 2 to the third power is 8. 3 to the third power is 27, which is already more than half of this, right? So it must be 8. And it actually is. It's 8 times 5. So this is the third root of 8 times 5. Okay. And I can take the third root of 8. What's the third root of 8? If you don't know by now, hopefully you'll know it soon. It is 2. And so that leaves me with 2 times the third root of 5. You really do need to start learning your perfect cubes and perfect squares, especially for the first, 5 or 6, if you can. All right, rewrite as a rational exponent. So I'm going to take the root and the power, and I'm going to put them in the right place. So remember, the top number is the power, the bottom number is the root. So it's 3 on the top and 4 on the bottom. An easy way to remember this is, remember with a fraction, the number on the bottom is what you're dividing by. So 3/4 literally means 3 divided by 4. Well, dividing, usually we think about that as making things smaller, just like with a root. A root is kind of like repeated division in the same way that exponents are repeated multiplication in a sense. So the top is what you're multiplying by, the bottom is the root. That means the top is the exponent, is the power, and the bottom is the root. Okay, and then evaluate. What that means is they want us to actually figure out what is this, but we want to do it by hand. I don't want you to just type this in your calculator. I want you to show that you understand what we did here by working it out down here. So you always want to take the root first if you can. So can I take the square root of 25? The bottom tells me the root, right? So I take the square root of 25. Well, that's just 5, and it's still to the third power. And what's 5 to the third power? That's 125.